colleagues again. Thanks for all of you who is still with us. And the fourth session of our workshop is devoted to advanced spectroscopy techniques at DESY. And I would like to notice at the beginning of this session that when 2 years ago we tried firstly to estimate how many active synchrotron users are in Ukraine and what synchrotron facilities they are using, we found that the most of Ukrainian users, probably from 30 to 50%, are doing their experiments in DESY. That is well understandable because DESY for a long time was the closest synchrotron facility to Ukraine. And a lot of Ukrainian scientists doing experiments in DESY then stay, work in DESY and bring their efforts and their experience to DESY. And our next speaker, Andrei Hluskovsky, is I'm afraid to say, but maybe he is the most prominent Ukrainian scientist in DESY, paid more than 15 years of their career to development of beamlines in DESY, and his talk is devoted to X-ray photoelectron spectroscopy at DESY.
Yes, thank you very much, Oksana, for your kind introduction. Hello, everybody. Do you see my slides?
Yes, we see.
Ah, lovely. Okay, then I start. Yes, good afternoon. Thank you for staying for my talk. And I will be speaking about hard X-ray photoelectron spectroscopy at DESY. And okay, good. Yeah, so we are located in the north of Germany, in the city of Hamburg, and Petra 3 is the high Blurians third generation radiation source, and it is 2.3 kilometer long ring. And at the moment we operate 25 beamlines, which open for users. You can see our portfolio at Photon Science webpage. And these beamlines are spread in 3 experimental halls. So the first hall was opened in 2008, and then immediately we started Petra extension project, and 2 more experimental halls arised within this project. So this is the layout of our P22 beamline, which is dedicated to photoelectron spectroscopy, and our beamline is very simple. We have an undulator, then double crystal monochromator with 2 pairs of silicon crystals. If users do need better energy resolution, we have a post-monochromator, which is also a pair of 2 more silicon channel cards. After this, we have a phase retarder to produce circularly polarized light, and a pair of mirrors for horizontal focusing, and very close to the experiment, we have the first pair of mirrors for vertical focusing, and at the experiment, we have the set mirror for horizontal focusing. And as you see, we are sitting quite far away from the source. Our experimental height is more than 80 meters from the source. So here are the energy characteristics of our 2 crystal pairs. In the double crystal monochromator, we start at 2.4 kilo electron volts, which is the minimum for crystal optics, and we cover the range up to 12 kilo electron volts. And as I told, if you need to have better energy resolution, we have additional post-monochromator, and at every excitation energy, we can offer the energy resolution, which is pretty well enough for solid-state spectroscopies, which is better than 200 millielectron volts. And we operate four end stations at our beamline. And the first one is kind of workhorse instrument. This is the hemispherical analyzer for hard X-ray photoelectron spectroscopy. The second instrument belongs to the Stockholm University, to the group of Anders Nilsson and his successor Martin Beyer. And this setup is basically doing the same experiment, but at ambient pressures. And our pressures are possible in this chamber are up to ambient pressure, up to 2 bars. And then we have 2 microscopes for doing spectroscopy with lateral resolution, namely hard X-ray photoelectron microscope for full field microscopy to resolve chemical and magnetic structures. And our latest development in the collaboration with universities of Mainz and Würzburg is the momentum microscopy. This is kind of hard X-ray angular result spectroscopy. Let me briefly introduce you the method. It's photoemission is a photon in electron out process. We irradiate the sample with the monochromatic light with known energies, and we kick out the electrons out of the solid and analyze their kinetic energy. And knowing the excitation energy and measuring the kinetic energy of photoelectrons, we get the information about binding energies of the electrons in the solid. And since each element has a unique set of Cora levels and Cora level energies, the photoelectrons are the fingerprint of elements. So we can do the non-destructive chemical analysis of our sample. And photoelectrons carry quantitative information about other goodies like band structure, oxidation state, magnetism, and spin of the materials, and many others. So here I have to explain you why we are keen of using hard X-rays for photoelectron excitation. For this, you have to look at the universal curve, which describes the electron inelastic mean free path. This means that this is the distance traveled, mean distance of the photoelectrons traveling in the solid without scattering events, without inelastic scattering events, depending on the electron kinetic energy. And you see that in the VUV range, the electrons are traveling about 1 nanometer without scattering events. In soft X-ray range, it's about 2 nanometers. This means that soft X-ray spectroscopies are very good for surface science. But if you want to study bulk electron properties, you have to go to hard X-rays. And this is the example which compares laboratory XPS and hard X-ray photoelectron spectroscopy spectra from kind of a half TMR junction, which is cobalt, iron, manganese, silicon, evaporated on MgO substrate, and then you have a kind of buffer layer, MgO and capping layer. And if you use the laboratory source, you do see only signal which is coming from the capping layer. And using 6 kilo eV excitation, we do get signal from the interface and from the bulk of cobalt, iron, manganese, silicon film, which is buried underneath capping and buffer layer. So conventional photoelectron spectroscopy is good for surface science, but if you want to study complex correlating materials with large unique cells and with completely different properties of surface and bulk, or you want to study real devices which are usually multi-layer thin films, including magnetic layers, studying, for example, buried layers, interfaces, magnetism effect, you have to go to high excitation energies. Also, very good news for users that we don't really need a surface preparation. We can use ex situ as grown prepared samples without any sputtering or cleaving if needed. Or we can also use operando devices like ferroelectrics, which do need an upper electrode to switch the devices up and down. And our electrons from operando devices can penetrate through upper electrodes. Yes, as soon as we are bulk sensitive, we can, of course, benefit from non-destructive depth profiling of our samples, and you can do it basically in 2 ways. You can increase the excitation energy from, say, 3,000 to up to 6,000 electron volts, and this is the standard example. Natural silicon oxide on silicon, and you see at 3000 EV excitation, the signal from the oxide is about the same as from the bulk, but when you increase the energy, then the signal from the bulk of the film dominates over the capping silicon oxide layer. And second possibility to do depth profiling is to change the takeoff angle of the photoelectrons by simply rotating the sample about the surface. The trick is that if electrons, if the sample is perpendicular to the analyzer, grazing incidence, normal emission, then the electrons are traveling using the shortest way to the detector. And in this way, we have bulk sensitivity. And if we rotate the sample, then the electron have to travel longer to the detector, and this enhances the intensity from the capping layer from the surface. So, of course, going to high excitation energies, and in this case, for higher kinetic energies of photoelectrons is not for free. We have to count with strongly reduced intensity, which is because the photoionization cross-section of the electrons decreases with the excitation energy, and also it decreases faster for higher angular momentum quantum number. This means that if for lower photon energies the spectra are dominated with F and P lines, in hard X-ray excitation, the photoionization cross-section drops down for F lines, and the intensity of the spectra is dominated by S S&P lines. But this can be used for our benefit because we can utilize it to modulate partial density of states in the valence band if we are interested in the subshell contribution to the intensity of the valence density of states. We can vary the excitation energy. So you see here that at low excitation energy, the intensity of 4 levels is the highest, and then with increasing excitation energy, the relative intensity of S states goes down, and the relative intensity of S, P, and D states dominates in the spectrum. So as I told, we have 4 instruments at our beamline, and the first instrument is the large hemispherical analyzer, which can analyze photoelectrons up to 10.5 kiloelectron volts. It has a large delay line detector with 65 millimeters microchannel plates to detect all possible electrons after the exit slit. And we offer multi-platform experiment control, which controls both our beamline and analyzer. And also we have a lot of software for simulating the photo emission spectra and for analysis of the spectra for fitting them to Gaussian and Lorentzian shapes. And yes, this is our manipulator. It's old good Omicron XPD manipulator, which has got 5 axes, X, Y, Z, and 2 rotations, polar and azimuthal. It has got a cryostat, also button heater to heat up the samples up to 400 Kelvin. And also what is special in our design, we have got 4 electrical contacts at the manipulator head, which end up in air, so we can apply bias to up to 4 samples in the manipulator to study ferroelectric samples. Or we can also measure IV curves during or right before the experiments. Also, we offer offline excitation sources like electron gun for ill spectra to study plasmon losses of the sample, and very standard double anode X-ray source for lab XPS if we are in shutdown or if the synchrotron is offline. Here is our load lock and distribution chamber. So we load the samples to the load lock, which is permanently vented, and the distribution chamber is always in UHV. It can carry up to 12 samples. And the load lock serves as a preparation chamber. We offer also wobble stick with cleaver if you want to prepare the fresh surface for your sample, or if you study the hydroscopic samples or kind of solar cells or lithium batteries, which have to be mounted in the argon atmosphere, we can transfer the samples in the noble gas atmosphere and dock them to the experimental chamber. Or you can, as a user, you can come with your own chamber, like MPI did to study uranium samples. They wanted to cleave them, and we of course asked them to come with their own cleaving chamber because we didn't want to have the pieces of uranium in our load lock. So they came, they cleaved their samples, and they removed their rubbish after the beam. As I told, the software, I think SESA is now free downloadable from the NIST website. You can simulate very well the shape of the photoelectron spectra. You can define the composition of your sample, in this case, cobalt, chromium, iron, aluminum, and then the substrate. Then you define the geometry and excitation energy, and you get black curve simulated spectrum. So you more or less know what you expect to see during the experiment. If you want to come prepared, or if you don't have the possibility to pre-characterize your sample in your home lab. And let me show you a few very simple examples. First one is about lead telluride thermoelectrics. It's very important material for thermoelectric people. They always improve the figure of merit of thermoelectrica, and apparently the carrier concentration is very important for figure of merit. And this was very simple experiment and very easy. We got two samples. One was lanthanum doped lead telluride, and one was iodine doped lead telluride. And one of them had slightly larger carrier concentration, and we saw that the Fermi energy of in the valence band of lanthanum doped sample was shifted of about 0.1 electron volt, which means that lanthanum doping leads to increase in the electron effective mass, because their concentration of electrons was almost the same in both materials. And this was apparently a very important result about the electron effective mass, and we contributed to this paper. And after 1 hour of measurements, it was a figure for the paper which received now more than 300 citations. But not all the experiments are so quick and easy. Here is one more example about the degree of delocalization of F electrons in uranium compounds. People always puzzled with the nature of F electrons in uranium compounds. They don't know either they are delocalized as D states, or they are localized as F states. 5F electrons, they have kind of mixed valency. And we took two counterparts, uranium gallium sample and uranium boron sample, which do have two different, which have the same ground state, but ground state symmetry, but two different lattice parameters. And uranium boron 2 was expected to be itinerant, because it has very small lattice parameter. And in case of uranium gallium 2, we expected that the electrons are much more localized on uranium atoms because of larger unit cell, and because of ferromagnetic ordering. And indeed, in the hard X-ray spectra, we saw a clear difference between 4F states. In case of UB2, the 4F states behave like metallic. They are kind of itinerant states. And in case of uranium gallium sample, we see the very clear multiplet splitting which is the hint for strong coupling between the electrons. And of course, the theory is a bit more complicated on this matter, and we have got a theoretician who simulated all possible number of F electrons, and he elaborated a statistical model. And indeed, it was proven that uranium-gallium-2 sample is F2-like with two localized electrons, and UB2 is more itinerant and band-like material with a number of F electrons which is between 2 and 3. And the same group took another series of uranium compounds, namely uranium metal silicon compound with palladium, nickel, ruthenium, and iron, which exhibit a variety of magnetic properties, but having the same ground state symmetry, and based on 4F photoelectron spectra, they were able to determine the valency of 5F electrons. The second experiment is, as I told, the ambient pressure XPS, and these devices operated in collaboration with Stockholm University. It's basically the same spectrometer, but the design allows the pressures up to 1 bar. And this is the very clever idea of Peter Amann, who is now at Syngenta company. He reduced the distance between the front cone and the sample, and the gas is fed through the jets. So we create the pressure at the sample position, while at the fast pumping stage we have already a distant vacuum of 10⁻⁴ millibars. And then the electrons, when they travel towards the detector, they arrive at good vacuum. The trick is that the distance from sample to the front cone is very small. It's about 50 microns or even less. And we offer also gas mixture, which allows us to mix 5 gases simultaneously. And this is a bit complicated experiment. So if you want to apply for a beam time, you have to collaborate with the Stockholm University, because it's not so user-friendly, but it's very productive machine. You can study catalysis, for example, rhodium crystal with 2 different orientations. You expose it to CO-NO mixture at different temperatures, and you can see that 111 surface has higher ignition temperature, for example. Now we come to microscopy experiments, and the proof of the principle was done about 10 years ago. This is the standard photoelectron emission microscope, but combined with the hemispherical analyzer, so you can get the image of your sample with energy resolution. Very simple principle. For example, here we detect the intensity underneath of chromium wedge from gold sample, and we see that the imaging works pretty good, and spectroscopy information corresponds to gold underneath chromium. Or you can also study the ferroelectrics. You can see the pads clearly, and if there is an STO sample underneath gold electrode, the red pad was switched, and the blue one is a bare substrate. You can localize them in the microscope, and then you extract their spectral information from them. And you see that the interfacial states at the electrode are different from bulk electronic states. Also, you can study.
Time is going.
Yes, yes. So I'm wrapping up. Stainless steel, you can see different grains and also can detect subtle variations in the grains. One more bright idea is the momentum microscope, and it's based on the fact that every electrostatic lens has an angular image in its backfocal plane. So if you then afterwards somehow do the energy dispersion of the photoelectrons and image not the Gaussian plane but backfocal plane, you receive the 3D Kx, Ky, and energy image cube at your detector. And this is how the bands are looking like. And the experiment is pretty fast. You can acquire the full 3D K-space in about 30 minutes. And also this microscope can work in the PIM mode, but the resolution is not as good as momentum resolution. So I will skip XPD session, and fortunately we listened already to Piotr today. DESY is a part of Nephews Consortium, so please do not hesitate to contact our users office if you get the beam time at DESY, and that's how you can apply for the beam time at P22 via enrolling access mode. So you can apply for the beam time at almost any time, and your proposal will be considered and evaluated almost instantly. And with this, I'm sorry for a delay, and I thank you for your attention, and please contact us if you want to apply for the beam time. We are looking forward, Ukrainian users. Thank you very much.
Thank you very much, Andrei, for a nice presentation. Probably one short question, if any. No.